Welcome to IPDPS 2020. This is Distributed Graph Realizations by John Augustine, Kirti Choudhury, David Peleg, Sumati Sivasubramaniam, Suman Sorev, and myself, Avi Cohen. What are graph realization problems? In general, graph realization problems deal with constructing graphs that satisfy certain specified properties. A classic, well-studied example is the realization of graphs with a given degree sequence. Given a sequence of node degrees as input, the first goal is to decide whether this sequence is realizable. That is, whether it is possible to construct a graph with the specified sequence of degrees. If so, the second goal is to realize such a graph. If not, output unrealizable. In the sequential setting, this has been solved back in the 50s by Havel Hakimi. In our work, we consider this problem and other graph realization problems in the distributed setting. Our motivation comes from peer-to-peer networks, where overlay networks need to be constructed repeatedly. And sometimes we would like to ensure good properties such as bounded degrees, small diameter, or good node connectivity. Before discussing our model and results, we briefly discuss the Havel Hakimi algorithm that inspired our main algorithm. We start with a sorted degree sequence. Each element is assigned a node in the target graph. We then connect the first node, A in the example, to the three nodes that follow it in the sorted order, B, C, and D. We then compute the residual degrees and resort the sequence. Notice that now A has the three neighbors it needs. This describes a single phase of the algorithm, which we next repeat. The second phase starts with the sorted sequence in purple, and the top node now becomes B. B is then connected to nodes E and C that follow it in the sequence. We obtain the residual degree sequence again. Again, we resort. Now E is the top node. We connect E to D, and the residual sequence is empty. So we are done, and we output the result. This is the fully realized graph we get as an output. To recap, in each phase we start with a sorted sequence, satisfy the requirements of the first node in the sequence, compute the residual degrees, and resort to obtain a new sorted sequence. The algorithm terminates in two cases. One, the sequence becomes 0, and then we output the constructed graph, as we did here. Or two, one of the elements becomes negative, which remarkably can only happen if the sequence is unrealizable. So we output unrealizable. For our distributed model, we consider the node capacitated clique model, NCC, recently introduced in SPA 19. The NCC comprises n nodes that can communicate with each other via synchronous message passing. Each node is uniquely identified by an ID. We mostly assume an integer between 1 and n. A node can send at most O of log n messages of size O of log n bits per round. However, in order for a node V to send a message or create an edge to another node U, V must know the ID of U. Intuitively, U's ID can be viewed as its IP address. We distinguish the NCC setting into two variants, NCC 0 and NCC 1, based on the IDs initially known to the nodes. In NCC 1, which matches the NCC model introduced in SPA 19, all nodes have full knowledge of each other's IDs. Thus, this version of the NCC is similar to the KT1 variant of the congested clique model, except with a bound on the number of messages that can be sent or received at a node in every round. In NCC 0, on the other hand, each node only knows the IDs of a few other nodes. Formally, each node knows only the IDs of its neighbors in some directed initial knowledge graph. For concreteness, in this work we assume that the knowledge graph is a directed path consisting of n nodes arranged in some arbitrary order. Our deviation from the standard congested clique model is in the interest of being useful in the peer-to-peer context. Realistically, the number of messages each machine has the capacity to send and receive simultaneously should be limited. Additionally, the NCC 0 variant we introduce allows us to take into account cases where nodes have partial knowledge of the network. The problem. The first problem we consider is the distributed degree sequence realization problem. In this problem, each node Vi gets an integer di signifying its degree in the target graph G to be realized. The goal is to construct a graph G with a degree sequence d1 to dn. The second problem we consider is the distributed connectivity threshold realization problem. In this problem, each node Vi gets a vector of integers, sigma Vi V1, sigma Vi V2 to sigma Vi Vn, signifying the connectivity requirement Vi has to each node, other node Vj. The goal is to construct a graph containing at least sigma Vi Vj edge disjoint paths between each pair of nodes Vi and Vj. We consider realization in distributed setting in two ways. The first is explicit realization, that is, each edge uv is known to both the nodes u and v, and implicit realization where each edge uv is known to at least one of the endpoints u or v. That means that it's possible that I don't know of a neighbor I have, but that neighbor knows that he is my neighbor. Some related work. As I mentioned, NCC is a variant of congested clique introduced by Lotker et al. In 2005. In our distributed setting, for the problem of realizing degree sequences, Havel and Hakimi independently came up with the recursive algorithm we showed in the beginning of this lecture. Non-centralized versions of realizing degree sequences have been studied in the PRAM model of parallel computing by Arikati and Maishwari. Our algorithm for connectivity threshold was inspired by the sequential algorithm of Frank and Cho. And finally, our algorithm for realizing trees of minimal diameter was adapted from the greedy tree algorithm of Smith et al. Primitives we use in our algorithms. We use several previously established primitives for the NCC model. Each can be implemented to run in polylogarithmic number of rounds. Recall we assume the knowledge graph starts out as a path in the NCC0 variant. A balanced search tree can be constructed from any connected path. Using such a search tree, we can sort a path. That is, in the context of degree sequences, for example, we can sort the nodes in non-decreasing order of degrees without broadcasting all degrees to all nodes. A node knows its position in the path and can use the search tree to message another node by its position on the path. Broadcast and aggregation can be done globally, but interestingly, in spite of possible issues of congestion, it is possible to simultaneously broadcast from O of log n distinct sources, each within a distinct subgroup of nodes. The distributed degree sequence realization algorithm. Recall we start with each node knowing only its own degree in the graph to be realized. Using the sorting primitive, we sort the nodes according to their degrees, constructing a sorted path graph. We then find the currently largest degree, delta. Here it is 3. We group all nodes of degree delta into Q groups of delta plus 1 nodes each. Here we only have one group of 4 nodes. In each group, the leftmost node creates edges to every other node in the group. Here, A creates edges to B, C, and D. By creating an edge, we mean it broadcasts its ID to them. If Q is larger than 1, we can use the multicast primitive to complete all Q broadcasts simultaneously in O of log n rounds. We next resort the path graph and repeat the process. The newly sorted path graph consists of 3 nodes of degree 2. So now the largest degree is 2, and we have one group of 3 nodes of degree 2. So all we need to do is connect B with C and with D by sending the ID of B to C and D. Again, we resort and repeat the process. Now we have two nodes of degree 1. The largest degree is 1. We get one group of two nodes. So all we need to do is connect C to D by sending the ID of C to D. The realization is, unsurprisingly, the 4-node clique. Notice that Havel Hakimi took care of the needs of one node in each phase. Our algorithm takes care of multiple nodes simultaneously each phase. Additionally, notice that the maximal degree delta decreases by at least 1 in each phase. Time complexity. The number of iterations in the implicit realization of this algorithm is O of minimum delta or square root m, where delta is the maximum degree in the sequence and m is the number of edges in the final realization. Proof idea. So the first fact is that each step handles and removes all nodes of current maximum degree. So notice that in each group we created, the leftmost node has been removed and the rest of the nodes have the degree reduced by 1. So the number of iterations can be at most delta. Fact 2. In any m-edge graph, the number of nodes of degree larger than square root m is at most O of square root m, just by a counting argument. In each iteration, the degree of at least one node of maximum degree becomes 0. So the number of iterations required to remove all nodes with degree larger than square root m is at most O of square root m. For the remaining nodes, they have degree at most square root m by definition, so the O of delta bound translates to an O of square root m bound. Realizations of trees. We present two algorithms. Both of them construct a tree in a single phase, provided the sequence can be realized as a tree. As before, we start by sorting the degrees. We next test whether the sequence can be realized as a tree. This can be done easily by aggregating the sum of node degrees, because the sum of degrees of an n-node tree must always be 2 times n minus 1. We next divide the nodes into non-leaf nodes and leaf nodes. The basic construction, we start by creating a path between the non-leaf nodes. So we connect each non-leaf node to the node preceding it and the node succeeding it, provided they are not leaves. We next assign each non-leaf node its required number of children in parallel from the leaves. The time complexity is log cubed, which is just the time complexity needed to sort the sequence. So consider, for example, 4, 2, 2, 1, 1, 1, 1. We start by connecting 4, 2, and 2. Now, 4 needs 3 children, which it takes from the leaves. The first 2 doesn't need any more children, and the second 2 needs 1 more child. We conclude with the following realization. The connections can be done in parallel using the aggregation the multicast primitive. Now we consider another construction which has a minimal diameter guarantee. In this construction, for each non-leaf node with x required children, we assign V the x nodes immediately to its right that are not in the tree. The time complexity is again log cubed, and it is not required to start by creating a path. So again, the same examples. So we start with the 4. The 4 is connected to the 2, and the first 1, 2 ones. All that is left is to connect the first 2 to the third 1 and the second 2 to the last 1. Now, notice that we did this in 2 phases, but this can actually be done In parallel, we can compute locally what the degrees, what the positions of the nodes that need to be the children of each node, and then multicast the ID of each node to its children simultaneously. And this is the realization that we get. The last algorithm we present is the connectivity threshold realization algorithm. Recall that in this problem, the input to each node is a vector of connectivity requirements to each of the other nodes. Connectivity being the number of edge disjoint paths between two nodes. So let sigma uv indicate the required number of edge disjoint paths between u and v. We define rho v as the maximum on all nodes u of sigma uv. Our algorithm guarantees that the number of paths between u and v is at least the minimum between rho u and rho v. So we start by finding a node with the highest rho value. Say this node is W. Each node different than W then chooses an arbitrary set of rho v nodes that always includes W. The above procedure gives a 2 approximation on the optimal number of edges needed for the guarantee to be met. That is, the number of edges added is at most twice the number of edges necessary to satisfy all the requirements. We skip the proof of this statement, but prove the connectivity guarantee is indeed met. Proof of correctness. Consider two nodes U and V. Let x1 to xl be the shared neighbors of U and V. Let u1 to ur be the nodes that are neighbors of U but not of V, and v1 and vk to vk be the neighbors of V that are not neighbors of U. Notice that all nodes are neighbors of W. Now, for every I, there is a path u xi v. So this gives us L disjoint paths. And for every I, there is a path u ui w vi v. So this gives us minimum R or K paths, additional paths. In total, we have at least the minimum between the degree of U and V paths. But since we guaranteed the degree of U and V to be at least rho U and rho V respectively, this means that there are at least the required number of paths between U and V. Thus concluding the proof of correctness. We next give a brief presentation of our lower bounds without proof. Notice that all of our lower bounds are tight up to log factors with the algorithms we present. In explicit realizations, any distributed NCC0 algorithm for realizing a degree sequence requires at least omega of delta over log n rounds, where delta is the maximum degree. In implicit realizations, any distributed NCC0 algorithm for realizing degree sequences of m edges require at least omega of square root m over log n rounds. And finally, any distributed NCC0 algorithm for realizing degree sequences of maximum degree delta in NCC0 requires at least omega of delta rounds. To summarize, we have initiated the study of graph realization problems in the distributed setting, presented efficient algorithms in the NCC model for realizing overlay networks that satisfy degree or connectivity requirements. We believe that such formal study of overlay network design may facilitate the design of a wide range of fundamental tools with strong guarantees. In addition to building such theoretical foundation, we hope our line of work may produce new ideas leading to practical improvements in building overlay networks. Our work also opens up a number of interesting new directions for future exploration. Overlays need to be robust against a wide range of failures. Modeling these requirements in the form of properties that must be satisfied in a graph realization problem could lead to interesting directions not studied so far. Additionally, it will be interesting to realize graphs from specific suitable graph classes. We have considered the realization of trees, but we believe that realizing graphs in other classes like planar graphs or total graphs can also be of value. Thank you for listening.